Atomic energy now silently furnishes power for the production of electricity. This reactor, liquid sodium coolant, flows into the reactor at the bottom of the core tank. From there, it flows past the hot fuel elements to an upper pool and out of the top. The radioactive coolant is pumped through a primary loop and returned to the core tank for recirculation. The heat from the sodium in the primary loop is transferred by a heat exchanger to a secondary loop, which is non-radioactive. The heat from the secondary loop can be exhausted to the atmosphere by an air blast heat exchanger, or it can be utilized in a steam generator. The steam drives a conventional turbine generator for the production of electricity. The steam plant can produce 6,500 electrical kilowatts, with the reactor operating at its design power level of 20,000 thermal kilowatts. Prior to and during the construction of the SRE, Atomics International engaged in extensive test and development work on reactor components. Early studies were conducted to determine the physics characteristics of SRE fuel elements. For these tests, mocked-up fuel elements were irradiated in the thermal column of a research reactor. A hydraulic loop was used to simulate sodium flow conditions around a fuel cluster. These tests provided data for the most effective location of fuel element accessories. A full-scale mock-up of the fuel handling system was checked out mechanically. The fuel hoist and electrical interlocks were operated through a series of tests in which fuel elements were raised and lowered an equivalent length of the core. The operating characteristics of prototype coolant pumps were studied through the use of a high-temperature sodium loop. Sodium has proven particularly suitable for use as a reactor coolant because of its excellent heat transfer properties and high boiling point. Another test loop was set up to prove the compatibility of sodium coolant with the zirconium used for moderator cans. Because of low operating pressures, combined with the choice of materials which are compatible with one another, the SRE is an extremely safe system. Fuel elements for the first core loading were made from slightly enriched solid uranium slugs contained in 7 rod clusters. Each rod consists of a 6-foot-high column of 6-inch slugs. A thin-walled stainless steel jacket encloses the slugs. To obtain the best possible conditions for heat transfer from the fuel slugs to the jacket, a sodium-potassium bonding medium was used. The bonding material was admitted under an inert atmosphere. The jacket was sealed at each end by a welded stainless steel plug. Ultrasonic inspection was employed to check the uniformity of bond between slugs and the jacket. To prevent the fuel rods from touching each other or the coolant channel within which they are suspended, the 6 outside rods were spirally wrapped with stainless steel wire. This provides clearance around each fuel rod for passage of the sodium coolant. Among the most unique fabrication techniques were those associated with the moderator assemblies. Reactor-grade graphite was machined into a hexagonal shape before being sealed in zirconium cans. The moderator cans were fabricated from 6 separate longitudinal panels of zirconium. The formed panels were machined to the specified width. A heliarc welding stake was used for the longitudinal welding. The seams were fused together without filler rod to assure a minimum of contamination. All moderator cans were thoroughly leak tested, since a leak would allow absorption of sodium by the graphite and cause excessive neutron losses. The welds were also X-rayed to check for porosity and contamination. Three graphite blocks comprise the moderator element for each can. Short sections of moderator cans were used to determine the durability of welded head assemblies. Through these tests, improvements were made, and final heads survived tests equivalent to 8 years of operation in the SRE. A stainless steel grid plate near the bottom of the core tank supports and precisely locates the moderator assemblies. These holes space the lower ends of the moderator cans and fuel elements on an 11-inch triangular lattice. The core is contained within the stainless steel core tank. Its walls are 1.5 inches thick. The bottom head was formed cold and heat treated. The sides of the tank were built of 3 ring sections, each welded in place. The thermal shield surrounds the core tank. It was made of 7 individual rings cast from low-carbon steel. Its function is to absorb most of the heat due to gamma rays and neutrons, and to protect the concrete shield from thermal damage. The rotatable top shield is 6 feet deep. Removable plugs, which extend through the shield, permit access for the installation and removal of any fuel or moderator assembly within the core tank. This shield is filled with dense concrete and provides radiation and thermal shielding directly above the reactor core. The sodium pumps are modified hot oil pumps, similar to the type used in oil refineries. Principal modifications consist of vertical mounting and the addition of sodium seals at the shaft and at the case. In mid-1954, concurrent with the fabrication of components, preparation of the SRE site was started. The first major item to be installed was the core cavity liner. It serves as a form for the concrete foundation and is located below ground level. Steel pipes welded to its outer surface provide a means of circulating coolant to remove heat from the surrounding concrete. The large circular holes accommodate sodium inlet and outlet piping to the core tank. Enclosed cells, also beneath ground level, are provided for cleaning and storing fuel elements. A hot cell houses the facilities for examination and disassembly of any radioactive component from the core. The upper 6 feet of concrete of the cavity liner serves as a biological shield. It was made from high-density concrete containing an aggregate of magnetite iron ore. A cylinder of 3 foot thick reinforced concrete formed around the remainder of the cavity liner provides a structural support as well as a radiation and thermal shield. 4 concentric rings were installed at the bottom of the cavity liner. The rings support as well as vertically align the outer tank and core tank. Before the installation of the outer tank, blocks of thermal insulation material were installed in the interior of the cavity liner. Fabricated from low alloy steel, the outer tank is 12.5 feet in diameter and 19 feet high. The bottom supports the core tank as well as the thermal shield. The thermal shield rings were stacked, but not welded to each other, to allow free expansion and contraction during reactor startup and shutdown. Practically all of the heat developed in the thermal shield is conducted back to the core tank. Perhaps the most impressive single SRE component is the stainless steel core tank. The core, or heart of the reactor, is housed within its walls. Within this vessel, molten sodium flows through the core at the rate of 1,200 gallons a minute to absorb the heat of the fission process. Stainless steel bellows seal the top of the core tank and outer tank. They maintain the sodium vapor within the core area and permit vertical expansion of the tanks. The moderator and reflector units were installed in the core tank under conditions of extreme cleanliness. The crew wore new uniforms and gloves to avoid contaminating the moderator units. During installation, the components were cleaned continuously with a high-capacity vacuum cleaner to remove any lint or foreign matter. With the moderator and reflector in place, installation of the top shield proceeded. Total weight of this shield is 75 tons. In this low-pressure system, there is no conceivable way in which the release of energy within the reactor could result in the dispersal of radioactivity in any significant quantity. The rate of coolant flow in the sodium loops is controlled by 4 pumps. Pump drive motors are located above floor level to facilitate inspection and maintenance. For the initial fuel loading, 33 fuel elements were installed in the core. Normal fuel loading consists of 43 fuel elements. The SRE was brought to criticality on April 25th, 1957. Reactor stability, which was investigated under various operating conditions, even exceeds design expectations. During a 17-hour steady-state test run, a timer connected to the control rod indicated that a total of only 2 minutes of adjustment was required. On the first full power run of the reactor and steam plant, all systems operated smoothly and full power was obtained with ease. Electrical power reached 5.8 megawatts. Thermal power, 20 megawatts. Main primary sodium flow rate, 1,200 gallons per minute. Main secondary sodium flow rate, 1,200 gallons per minute. Steam flow rate, 54,000 pounds per hour. Reactor inlet temperature, 560 degrees Fahrenheit. Reactor outlet temperature, 925 degrees. Sodium inlet temperature to steam generator, 835 degrees. Sodium outlet temperature from steam generator, 480 degrees. Steam temperature, 750 degrees. And steam pressure, 600 pounds per square inch. The data obtained from the first full power runs indicate the feasibility of operating the SRE well beyond the initial design specifications. During power runs, numerous measurements of shielding effectiveness were also made. The shield blocks above the radioactive coolant galleries and over the reactor core were found to be more than adequate. Other measurements made directly over gaps between shielding blocks indicated that radiation levels were well under the permissible value. Following power runs with the first fuel loading, an experimental irradiation program was begun. About 1/4 of the fuel elements are of an experimental nature. They include special uranium alloys, thorium uranium, and high-temperature ceramic fuels. This program is being conducted to develop longer fuel life and to increase reactor operating temperatures. Because the fuel elements become highly radioactive from reactor operation, used fuel elements are removed from the core by a shielded fuel handling cask. This 34-foot high chamber is suspended from a bridge crane. It is shielded by 35 tons of lead. A central tube, the length of the cask, accommodates 2 fuel elements. The operator positions the cask in the general area over the used fuel element to be withdrawn. An indexing mechanism then guides the cask to a preset position, precisely in line with the given fuel element. A pneumatic mechanism forces a lead radiation shield down onto the surface of the loading face. A gas-tight seal is made prior to withdrawal of the fuel element. A pickup device within the cask is lowered to engage the shielding plug of the used fuel element. The shielding plug, hanger rod, and radioactive fuel element are lifted out of the core as one complete unit. A revolving fuel support plate at the top of the cask is rotated 180 degrees to position the new fuel element over the empty fuel channel. The new fuel element is lowered into the core, and the shielding mechanisms are raised. The used fuel element is taken to underground cleaning cells where it is washed in a water bath. After cleaning, the fuel element, still highly radioactive, is transferred to a storage cell where its radioactivity is allowed to decay sufficiently to permit reprocessing. The hot cell is used principally for the disassembly and study of experimental fuel elements. It is also used for examining other irradiated materials, including moderator elements and control and safety elements. For some experimental work, the reactor is operated without producing electricity. Under these conditions, the heat is dissipated into the atmosphere by air blast heat exchangers. The hot sodium is cooled within this building as it passes through tubes located in the airstream of electrically driven fans. For electrical power production, sodium flows directly to the steam plant through the secondary non-radioactive sodium loop. As a safety precaution, the pressure in this secondary loop is greater than in the primary loop. Therefore, any leak would be toward the enclosed primary system. The electrical generating plant used in conjunction with the SRE was installed and is operated by the Southern California Edison Company. This plant is similar to a conventional steam plant, with one main exception: the steam generator. This single continuous unit converts heat from the secondary sodium loop of the reactor into superheated steam. The steam condenser is a conventional unit, supplied with 75-degree water by twin circulating pumps, drawing from an induced draft cooling tower. The conventional turbine generator feeds a step-up transformer, which raises the generator voltage to 69 kilovolts for transmission into the Edison distribution system. Although electricity is now being produced by atomic energy, additional technical development is necessary to achieve further reduction in costs. Competitive electrical power from the atom depends upon the production of useful heat in a reactor at a cost comparable with conventional methods using coal and oil as fuel. As a part of the Atomic Energy Commission's program to develop economical nuclear power reactors, this important experiment has confirmed the outstanding characteristics of the sodium graphite reactor. Operation of the sodium reactor experiment continues to provide constructive experimental data, demonstrating the technical success of this concept for use in central station power plants.